Alright guys, welcome back to another video. Today we're going to be talking about the different types of nucleophiles that we've encountered so far. We're going to start off with ones that involve carbon. This is just kind of a generic reaction mechanism that I've drawn up right here. And so what we're going to do is we're going to take a look. This is a Grignard reagent, one of the more common reagents, nucleophiles that we use when doing carbon-related nucleophile reactions. So basically this simple mechanism just shows how we bond the Grignard reagent portion to this carbonyl chain that we have, where the MgBr attaches to the oxygen and takes away that double bond, and the ring structure attaches to that carbon that has a space. And then with the addition of some hydrochloric acid and water, we then can get rid of the Grignard reagent part of the Mg and the Br and replace it with an H, creating an alcohol. So what we do here is we basically have created an alcohol from our original carbon chain that had just an oxygen beforehand, and we've also lengthened our carbon chain to include that ring structure. And this is a pretty simple reaction mechanism, but we can take these similar principles and move on to our nitrogen ones. So we're going to move on down to our nitrogen. Now our nitrogen ones, we have a couple different ways of doing this. So if we started with an aldehyde, as we're starting with right here, we can add this nitrogen compound here. And you'll notice that there's some lone pair of electrons on that nitrogen. And what we're going to do is we're going to put that in presence of hydrogen ions, or H plus ions, and those are going to come in and attack those electrons and create another bond where we then push those electrons onto the aldehyde, and that creates this thing called an amine. And you can kind of see and follow how the bonding works out, where the O and the H from the aldehyde initially were taken and made into a water molecule, and then the rest of the nitrogen compound was added to the aldehyde at the position where the O formerly was, and that's what we've created here is an amine. And if we were to do the same type of reaction but with a ketone, what we're going to get is an iminium ion. And as you can see, there's a positive charge right there on the nitrogen because it has formal charge of +1 because of the 4 bonds rather than just 3. And then what we can then do is we can push those electrons through and basically push that double bond out away from the nitrogen. And what we've created then is called an enamine. So similar to an amine, but then the double bond is one removed from the nitrogen, and that's what defines it as an enamine as opposed to an amine. Now, amines have the double bond attached to the nitrogen as the final product, where the enamines have it one bond removed, or one carbon removed from the nitrogen. Moving on down, we have our oxygen-based ones. So we're going to start off with this simple carbon molecule here, and we're going to put it in the presence of some water and sulfuric acid. And what that gives us is that oxygen is going to kick electrons from the oxygen onto this double bond, which is then going to kick it off over to this position on this carbon, and that's where the oxygen is going to end up attaching. And as we see, that double bond has gone away, and we also have the addition of a hydrogen over there. So you can kind of see where the water has gone. So you have the O and the H right there, and then the other H has gone up in here. And what that does is it really allows us to kind of create different chemicals with oxygens and creating carbon-oxygen bonds, which is super useful in a lot of organic chemistry. Moving further down, we have our last main example here, which is the formation of hemiacetals and acetals, which it can also be related to the formation of hemiketols and ketols. And hemiketols and ketols are the same general mechanisms as hemiacetals and acetals. You form them the same way, but our starting material would be a ketol, where in this case we have an acetal. Or excuse me, a ketone versus an aldehyde. So we have an aldehyde starting material in this case. But if we wanted to create a hemiketol and a ketol, we would start with a ketone starting material. So this mechanism, we put it in the presence of H plus ions, and then those ions are going to go onto that oxygen to create an OH group. And then we put it in the presence of methanol, and that methanol is going to come on, and it goes onto the oxygen where those free electrons were, and then creates a positive charge here, and then that OH group gets pushed aside. So basically what happens is the O has that free electrons, and they bond right there where that double bond is, and then the H and the Me are on that bond as well, and that's what creates that positive charge. And then once the charges have balanced out, we get this hemiacetal. And the reason it's a hemiacetal is because we have an OMe group and an OH group. Now an acetal is going to have only OMe groups, no OH groups, and that's why we call it a hemiacetal, is it's partially an acetal. So then we can kind of run through this reaction a second time, doing the same steps basically, and in that way we get a full acetal as opposed to a hemiacetal. So we just do that protonation step again, and the protonation goes through, and we go and we create water molecule on this where that OH used to be, and then once we've removed that charge down, moved it over, it's going to come in as an oxygen positive ion, and that also creates a double bond right here. And then we put it in the presence of methanol again, and that methanol is going to create another OMe group with on that positive charged oxygen, and add another hydrogen, and that creates our full acetal. Thanks, guys.